So Friday, we finished talking about significant digits, and we were working partway through this worksheet. But I did want to finish with the 7, 8, 9, and so on. So for number 7, looks like we're doing a subtraction here. And the key thing with subtraction, is it sig figs or is it number of digits to the right of the decimal? Which one's more important? To the right. So if we go back and we look at our rules, right? We've got this set of rules for math. And we said your results cannot be more precise than your least precise measurement. So basically, if you look to the right of your decimal in this example, and you see that that 0.25 only has 2 digits to the right, that means your answer can't have more than 2 digits to the right of your decimal. So let's go back and try to fill this all out. What do you guys think the best answer would be? A, B, C, or D? A? Yeah, A, if we look at it, we don't even need to do the math. We know it's got the proper number of sig figs in there. So A is definitely the correct answer there. All right, what about 8? Do we need to do sig figs or digits here? Sig figs, right? So which one has the fewest number of sig figs? The 923 or the 20,312? 923. It's got 3 sig figs, right? So we can go through process of eliminate D out because that one only has 1 sig fig, and we can cross B out because that has 2. Now the question is, which one is the best fit, A or C? What do you guys think? How many sig figs are in A? We've got 3, right? And C has 3, but which one's the correct answer? Does anybody want to explain why? What do you think?
Because in A, the problem would be if you went only to the left, then it would be 0.04, which is 2 or 1 sig fig. So it would have to be C because they're...
Okay. And the main thing with C, too, is we want to keep all of the digits that we can. It looks like with A, they just kind of left off some digits, too. So C is the most correct answer here. All right, if we go to 9, the mass of a watch glass was measured 4 times. The masses were as follows. What was the average mass of the watch glass? So there's a couple things we've got to do. First thing is we've got to average them, and then we've got to determine which one matches. But in order to average them, we need to add them all together and then divide them. If we're dividing them by 3, does that mean it only has 1 sig fig? No, because 3 is an absolute number. It wasn't a measured value, right? So if we look at this, it should go all the way out to 3 digits past the decimal. So we can say, well, this one doesn't work, this one doesn't work, this one doesn't work, but this one definitely does. So we're following the addition rules. Or by 4, excuse me. Yeah, I miscounted. All right, the next one. We've got a volume in a graduated cylinder. What does cc stand for again? Yeah, centimeters cubed. It's common in hospitals to see cc rather than centimeters cubed. All right, now the next question I have for you guys. Are we measuring up here or are we measuring down here? Down in the middle. We want to measure the bottom of that curve. What do we call that curve? The meniscus, right? So we need to measure the bottom of the meniscus. In this case, we've got hash marks for every 1 cubic centimeter, which means we want to estimate out 1 digit further. So in this case, the best answer would be B. All right, 11 is a little bit trickier. How many of you guys had a chance to do number 11 yet on your own? A couple people. I'll give you guys a minute to work on this, but what we want here is a number times 10 to the something's power. So for example, it might be 3 times 10 to the 2. The other thing is try to keep the number of sig figs the same. And if you think you got it, check with your neighbors too. If you think you got it, give me a thumbs up. Looks like we're about halfway there. So I'll give you guys a hint too. We've got this decimal that's assumed right there. We're going to move this decimal all the way up here. So is this going to be 10 to the 3, 10 to the 4? 10 to the 4, right? So all we're going to do is 6.15 times 10 to the 4th. All right, next one, we're going to move our decimal back over here. So it looks like we're moving at 1, 2, 3, 4, 5. Should we be 10 to the 5th? 10 to the negative 5th, right? So this would be 5.68 times 10 to the negative 5. All right, same thing over here. We've got an assumed decimal point here. We're going to move it 2 spots over. So it should be 3.21 times what? 10 to the 2nd. All right, same thing here. We've got a decimal. We're going to move it all the way over here. So it's going to be 6.496 times 10 to the what? 7. We moved it 7 places. All right, and then next one, we're going to move this to the right 2 places. So it's going to be 7.085 times 10 to the what? Negative 2. All right. Yep.
So, how do we know where to bring the decimal?
Anytime you write in scientific notation, you want your number to be essentially 1 or greater, but less than 10, right? So in this case, we don't want to say on the top one, for example, 61.5, because 61.5 is greater than 10. However, 6.15 is between 1 and 10. That's the standard scientific notation. All right, let's do a back page. Express the following in standard form, so non-scientific notation. This is pretty straightforward. So for the first one, we're going to just multiply it by 10 to the 3rd. You can use your calculator on any exam too, so if you're uncomfortable, don't worry. This would be 1090. Do I want a decimal point? Should I say 1090.0? No, the first number only had 3 sig figs, so we do not want that decimal point. We want to make sure our answer's got the same number of sig figs. All right, the next one is 10 to the 8th. That's a little hard to see on the screen. So this would be 422715000. So again, you want to keep the same number of sig figs, no decimal point. All right, the next one, we've got 10 to the negative 4th. So this would be 0.0003078. So everyone agree on that? It's a calculator problem. All right, next one, we've got 0.09004. And last but not least, we've got 518.74. So like I said, make sure you plug it into your calculator and that your answer has the same number of sig figs that you went in with.
Do we have to put the 0.0 or is it fine to just put 0?
That's a good question. So for this one, do you need that first 0? That's a good question. I see students all the time not have that first 0. However, it looks funny. I always prefer to have a leading 0 in front of my decimal. It just looks a lot better, and anytime you get into higher level math or higher level science, they want that first 0. Yeah. It's kind of nitpicky, but... All right, last problem. We've got multiplication. How many sig figs should our answer have for the first one? 3, right? So in this case, we can't have more sig figs than our number with the least number of sig figs. So both of them have 3. All right, if we plug this into our calculator, it comes out as 90060. And let's change this into scientific notation with the correct number of sig figs. What should it be? Yeah, so we've got this decimal point. We're going to move it here. So it'd be 9.01. We only want 3 sig figs. We're going to round up. It'd be times 10 to the 4th. And I always like to box my answer. That way I don't get confused. All right, the next one, if we plug it into our calculator, is 0.000000. So 3, 6. There we go. So we're going to move this decimal point over to the right. So what should this be for the answer, and how many sig figs should it have? Should have 2 sig figs, right? So it'd be 2.4 times 10 to the what power? How many places did we move it? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so it should be 10 to the 11th. Negative 11. All right, last one, and then we'll do more interesting stuff, I promise. All right, how many sig figs should this answer have? 2. Okay, so if we plug this in, the answer comes out to 124,000, which in scientific notation would be 1.2 times 10 to the what? 10 to the 5, right? We're going to move this decimal point that's right here all the way over here. So it should be 1.2 times 10 to the 5th. Make sense? Okay, occasionally what we'll do is work on these handouts. They're not meant to be handed in, they're just meant for practice. These are representative of what you might expect on the first exam. Extra copies are posted online, or if you want to just take one off the front desk here, you can use it as a review aid for the first exam. All right, we're going to try to finish up chapter 1 today. Hopefully we can get there. But the next thing we've got to work on is unit conversions. This is something that appears really easy when you first cover it, but it's easy to get tripped up on. So I'll show you guys the way I really like to do unit conversions. And I'll show you guys a simple analogy. Let's say you've got 2 dozen eggs. How many eggs do you have? 24, right? That's pretty simple to do in your head, but let's do it using math. And with unit conversions, what I do is I identify my units, which in this case is dozen eggs, and I need this unit to be in the bottom of my multiplier, right, in order to cancel it out. So for this next thing, I'm going to put dozen on the bottom. And we know our answer should have the unit of eggs, so I'll put eggs on the top. And we know that there are 12 eggs in a dozen, right? So does the 12 go on the top or the bottom? Would it be 12 dozen equals 1 egg? No. That's the number one mistake I see people make, is make sure that this unit essentially is the same as multiplying by 1. But we change the units.
What do you mean it's the same by multiplying by 1?
So 12 eggs is the same as 1 dozen, right? So 12 eggs divided by 1 dozen equals 1. So So in this case, it's not that we're multiplying it by a new number, we're just converting units here. So really, it's just a ratio. So by doing this, we can cancel out dozen. Cancel out dozen. That leaves us with only one unit left, which is eggs. So in this case, we know we've got 24 eggs. Okay, let's do a couple of other ones, and we'll do these with more scientific examples. Okay, for the first example, I've got 1.83 kilograms, and I want to know what this is in grams. So we know we're starting with 1.83, and our unit is kilograms. We want to cancel out kilograms, so kilograms should be on the bottom of our next multiplier. So I'll put it down here. The unit on the top should be what? Grams. That's the unit we're trying to find. Okay, now the question is, how many grams are in a kilogram, or how many kilograms are in a gram? Yeah, it's 1,000 to 1. So should 1,000 go on the top or the bottom? Top. So there are 1,000 grams in every 1 kilogram. So make sure that that number matches up with the unit. Okay, if we go ahead, we can cancel out kilograms and kilograms. And all of a sudden, we've got 1,830 grams. Let's do another one. This one's going to be a little harder. 162 pounds. I think that's roughly what I weigh. Don't tell anyone. And I want to know what I weigh in grams. This one's going to be a little bit trickier. But what you want to do is pull out that conversion sheet that I gave you last week if you've still got it. Let's set up our unit canceling first, and then we'll plug in numbers second. So pounds, we need to cancel out, so I'll put it on the bottom. We're trying to solve for grams, so it'll go on the top. We can cancel out pounds. That leaves us with grams. So we know we're canceling correctly. Question is, how many pounds are in a gram, or how many grams are in a pound? Does anybody see it on their conversion sheet? 4. All right, so 454 grams for every 1 pound. Okay, so our answer should have 3 sig figs in it. If we go ahead and we calculate this out, it's 73548 grams, which should be changed to what in order to follow our sig fig rules? Remember, we can only have 3 sig figs. So really, I'm just going to chop off these guys. And I'm going to say this should be 73500 grams. And then I'll box it to indicate that that's my final answer. Does that make sense? What's another way of writing this? Yeah, 7.35 times 10 to the 1, 2, 3, 4. So either one of these is acceptable, and on exams, I really don't care unless I specifically say presented in scientific notation. All right, let's do one that's a little bit trickier. This one's going to involve multiple conversions.
Why don't you put the zeros right there if it's on 3?
So for this top one, the question was, why do we have the zeros? Yeah, if we look at that top number in the box, it still only has 3 sig figs because there's no decimal. So it's not 735, right? It's 73,500, but it's still 3 sig figs. Yeah.
So if it was like, instead of 48, it'd be 58, would you have to round that?
Yeah, let's say the trailing numbers right here, if that number was 5 or greater, then you would round it up, right? So then it would be 736 for the first 3 numbers. That's a good question. Any other questions before we go to harder ones? All right, let's do a harder one. Okay. This one's a word problem. So what is the mass of 1.00 liters of gasoline? And I'll give you a value too. The density for gasoline is 0.703. And what are the units typically for density of liquids? Yeah, grams per milliliter. So we know we're starting out with 1 liter. And we're going to have a couple of conversions here. And we know our final answer needs to be mass units. So what's our typical math unit in chemistry? Is it grams or kilograms normally? Normally grams. So I'll just put grams over here. All right, there's a couple strategies you can use. One strategy is to kind of work backwards a little bit. So if we know our final answer is in grams, that unit's got to be one of the leftover units, right? All right. So the question is, this gram ratio, how can we plug it in with a number? Anybody have an idea? What do you think?
We have the density as grams per milliliters. We should put milliliters on the bottom.
Yeah, the only value we have right now with grams in it is this density unit. So we know for every 0.703 grams, we have 1 milliliter. That's good because that gives us our unit in grams. However, we need to cancel out this milliliter unit. So that means that milliliters must be on the top here. And what goes on the bottom? Liters. Okay, so let's just double check. We know units need to cancel out. So liters will cancel, milliliters will cancel. That leaves us with grams. We're in a good position now. All right, what's the ratio of milliliters to liters? Yeah, 1,000 to 1. So we've got 1,000 milliliters for every 1 liter. All right, if we plug this in our calculator, we get 703. I'm going to scoot this over. Does that have the correct number of sig figs? What do you guys think? I've got a question for you though. If we look at this one, this 1,000 right here only has 1 sig fig. Why doesn't our answer only have 1 sig fig? Yeah, it's not a measured amount. It's an absolute ratio. So in this case, your final answer should have 3 sig figs because our measured amount had 3 significant figures. Let's do another one. I'll let you guys work with a partner on this one. But you may need to do more than one conversion. How many joules of energy are in a 1,235 calorie hamburger? And remember too that this is an uppercase C. You may need that conversion sheet that I gave you. Or I guess it's in the notes. Sorry. It was 4.184 joules for every 1 calorie. However, the 1 calorie is the little c. Does anybody remember how you measure calories in a practical sense? So if I'm in a lab and I want to figure out how many calories are in a hamburger, how do I do it? I physically just burn the hamburger in a big tank of water and then measure how much the water temperature increased. It's called bomb calorimetry. That's an interesting food science. What's that? That's a good question. So in order for it to be measured using bomb calorimetry, you essentially have to burn it. How many people feel pretty comfortable with their answer here? Check with your neighbor too. Let's see a show of thumbs again. How many people feel confident now? If you feel a little bit shaky, you can put it like this. If you have no idea what's going on, give me a thumbs down. All right, there are some thumbs down. That's perfectly fine. This stuff can be really confusing when you run into multiple conversions. But let's just walk through it. So we've got our known unit, which is 1,235 calories with a big C. All right, first thing I like to do is make sure I cancel out my units. So I'll put big calories on the bottom. What should maybe go on the top? One problem I see is this hint that I gave you guys has little c. So maybe we need to convert our big calories to our little calories, right? Okay, so I'll put little calories up here. How many little calories are in a big calorie? 1,000, right? That's why in Europe, if you look on the food labels, they write kcal. It's a lot less confusing than looking for correct capitalization. All right, so we know that there's 100 calories in one big C calorie. Okay, that leaves us with the correct calorie unit, but we're not interested in calories, we're interested in joules. So now we need to cancel out calories and get to joules. So I'm going to put little calories on the bottom, that way we can cancel it out, and I'll put joules on the top. If we do that, that works out well because we can cancel out these guys, and that gives us our desired unit. But now the question is, where do we put that 4.184? Do we put it on the top or the bottom? on the top, right? Because it's a ratio. It's be 4.184 joules for every 1 calorie. I can plug this into my calculator. And does anybody want to help me with the answer?
5167.
5 point. What was it?
I got 5167,240.
Sorry, say that slower.
5167240.
Okay, how many sig figs should our answer have? 4. So what we can do is change this to our correct number of sig figs, and we can say, all right, 5167000 joules. That gives us our correct number of sig figs. What if we want this in scientific notation? So 5.167 times 10 to the what?
6.
So I'm going to take this decimal, move it 1, 2, 3, 4, 5, 6. All right, so that's 10 to the 6 joules. Does that make sense? So we're just moving this assumed decimal point 6 spots over. This is honestly one of the trickiest parts. Don't feel embarrassed if you're struggling with it. My organic students, I occasionally have to sit down and teach them how to do unit conversions again. It's really easy to invert numbers or not cancel out units correctly. Always, always, always show your units. And then double check that you've got your conversion factor the right side up. You don't want it to be inverted. Make sense? All right, there's, I think, one last section for this chapter. This talks about accuracy versus precision. What do you guys think it means when I say, wow, that person shooting their gun was really accurate? So they were on target, right? If you're accurate, that means that you're pretty close. So accurate, in a scientific sense, means that your average is close to the correct value. Whoop. The key word here is average. This is different than precise. What does it mean if you're precise? What do you think? Yeah, you hit something really close to the same exact point every time. Yeah, I think that's a great definition. So we'll call this a tight cluster of data. And I always like to view this as kind of target practice. So we'll make 3 different targets. Whoop, that's not very good. We'll imagine this is like an archery range. All right, for the first one, let's say I have 4 different shots, and they're kind of spaced out like this. Is that archer accurate, precise, both, neither? Accurate. I would say if you average all of those points, it's roughly close to the center. So this is accurate. But not precise. Versus this archer who clusters his 4 arrows in one corner. Would this be accurate? No. Yeah, it wouldn't be accurate because it's not close to the correct value, but it's clustered pretty tightly. So this would be precise. But not accurate. And then last but not least, we've got our good archer. Actually, let me clean this up. Who nails the bullseye with a tight cluster. This would be both accurate and precise. You have to be really careful when you use this terminology. Oftentimes it's misused. So you could say, wow, that person was really precise. That doesn't mean they did a good job, right? You could be really precise and be way off the mark. Yeah, consistently inconsistent is a good way of describing precise. Where accurate, also doesn't mean good. Your data could be accurate, but your error bars could be all over the place, right? So you want to have data that ideally is both precise and accurate. So data that is close to the actual value and doesn't have very big error bars. Yep.
So you have to choose between one or the other. Which one would be better?
Oh, that can be a little bit subjective, right? It really depends on your experiment that you're doing. There are some situations where you're really looking primarily for accurate data. And then there are other experiments where you can have precise data that's off the mark, but that's okay because you can adjust your experiment or variables a little bit. So this would be both. All right, at the end of every chapter, I like to do kind of a chapter wrap-up. And we'll turn this into kind of a Jeopardy-style questions and answers session. So for the first one, a key aspect of a scientific hypothesis is that it must be what? What is C? Good job, Ken Jennings. So that's a big problem, is oftentimes people come up with a hypothesis, but it's really just a guess. It's not something that they can go out and test. And hypothesis always has to be something that is testable, and it has to be something that could give you a negative result, right? So for example, if I drop a ball, my hypothesis be that it will go down. That means that there's an option at least of it going up, although we know that that likely won't happen. All right, next one. Which of the following processes represents a chemical change? So what is a chemical change? Let's define that first. What do you think?
Let's change like the properties of the chemical.
Yeah, so let's do a compare and contrast. A physical change is where we are not making and breaking bonds. We're just changing the state of matter or manipulating it in some way. Where a chemical change, we are changing the bonds, right? We're changing one type of matter into a new type of matter. All right, so water freezing into ice, is that physical or chemical? Physical. We're not changing the water, it's just changing states. All right, water evaporating, same thing, that's physical. Butter melts in a hot pan, that's still physical, right? It's still butter. You could let it cool and get your butter back. All right, a bicycle left outside begins to rust. That's chemical, right? Rust is a chemical reaction with iron where we form iron oxide, and we'll talk more about that later. Sugar dissolving in hot coffee, the sugar's still there, we haven't changed it. All right, what quantity represents the smallest mass? This one's a little tricky. So I'll give you guys a hint. If you are trying to compare these, make sure they're in the same unit. So what I would do is convert these all to grams, right? So let's do the first one. So to convert kilograms to grams, we know kilograms needs to be on the bottom, grams needs to be on the top. How many grams are in a kilogram? 1,000. So 1,000 kilograms in 1 gram, that means that this is 10 grams. We know that this one obviously is already in grams, so we've got 1 grams versus 10 grams. Oop. All right, 100 milligrams. Same sort of thing, I'm going to do a conversion here. We want to cancel out milligrams, so I'll put it on the bottom. We want grams, so I'll put it on the top. What number goes where? Yeah, there are 1,000 milligrams in every 1 gram, right? Oh. Okay, so if I plug this in, I get 0.1 grams. All right, same sort of thing here. And this would give me 1.0 grams. And then last but not least, I'll do this down here. We know for every 1 gram, we've got 1,000 milligrams. That gives us 100 grams. Those last 3 are pretty easy. All right, so now that we've got the same units, it's a lot easier to compare, right? So obviously the correct answer would be what? C. Okay, let's do the next one. So a 10-gram sample of which of the following substances would have the greatest volume? Once you think you got it, check with your neighbor. Share with your neighbor too. What's that?
Are we assuming they're all in the same state?
Yeah, they're all liquids.
Okay.
Or I guess copper in this case. Sorry, I didn't even see those. Copper and magnesium are solids, but they have their density listed. So it's a mixture of liquids and solids. Sorry. Let's see thumbs. Some thumbs sideways. All right, let's think about this just abstractly, no math. If I'm really, really dense, do I take up very much space? No, dense objects, just by their very definition, are compact, right? So they don't have a big volume. This one's asking which ones have the greatest volume. So conversely, things with low densities take up a lot more volume. That means that hexane, in this case, has the lowest density. You don't have to do any math for this one. It's just conceptual. Does that make sense? So if you think about a gas isn't very dense. It takes up a big volume versus a solid. That's a lot more dense. It doesn't take up as much volume. All right, the energy required to heat 1 liter of water from room temperature to 20 degrees Celsius or 20 degrees Celsius to boiling is what? This one's a little bit abstract. So let's go ahead and do unit conversion here. We know we've got 1 liter. And let's kind of define the amount of energy required, and I'll give you guys a hint. 1 calorie of energy can raise 1 gram of water by what? 1 degree Celsius. So let's try to set this up correctly. So 1 calorie of energy can raise 1 gram of water by 1 degree Celsius. Okay, so one problem I see is we've got liters, we need grams. So how can we convert liters to grams? Yeah, I would probably change it to milliliters first. So we'll put liters on the bottom, milliliters on the top. We know that there are 1,000 milliliters in 1 liter. That's good. So we've canceled out liters and liters. How can we go from milliliters to grams for water? So let's just plug in the units and then take a look at what these units mean. What is grams over milliliters? That's the density, right? Does anybody remember the density of water? 1. So 1.0 grams per every 1 milliliter. All right, that's good. So we've canceled out milliliters and milliliters. All right. And then last but not least, we need to cancel out grams. So we know we can raise 1 gram of water is 1 calorie with small c, so we can cancel out grams and grams. All right, and sorry, how many degrees are we trying to raise the water by to get it to boiling? 80, right? So boiling is 100 degrees Celsius. We're at 20 degrees, so we're trying to raise it by 80 degrees Celsius. And you can just put 1 on the bottom if you want, or just have it multiplied by 80. All right, and our correct answer for this one should be, whoops. what would it be? It'd be 8.0 times 10 to the fourth calories. So if we look at our answers, what's the problem? None of them match that. So let's convert it. If we look at 8.0 times 10 to the fourth, that's the same as what? So it's 80,000 calories, which could be what? 80 kilocalories, right? So really this is the only one that fits the correct answer. So some of these word problems can be a little bit tricky. I know a lot of you guys weren't able to take notes or at least draw out the whole problem, but log into OneNote. Everything I write on here is stored on OneNote, so you guys can pull it up and look at them that way. Yep.
You always put 1,000 over the starting.
Are you talking about the milliliters or? Yeah, so there's always going to be 1,000 milliliters in every 1 liter. Does that make sense?
So you always put 1,000 over 1.
Yeah, the key is both of those values need to be equal to one another.
Okay.
So for example, 1,000 liters is not equal to 1 milliliter. So you need to make sure you have the 1,000 on the correct side. All right, let's do one last one, and then we'll call it a day. Which of the following claims are falsifiable? A classmate claims that carrying an amethyst will increase your mental alertness. Or B, your fellow student claims to have memorized all of the element names and symbols. Or a self-help guru claims that your desire for success is strong enough, you will receive it. Or D, an alternative health practitioner claims that drinking energized water will promote cell health and increase moisture absorption in your body, resulting in increased vitality and overall energy. Which one? B. Yeah, you could quiz your friend, right? What's the problem with D? A lot of times people are tempted to select D. What does it mean to be energized, right? It means nothing. It's just a frou-frou claim. You see this all the time in grocery stores now. I went to a store recently where it was making all these claims about alkaline water and how much better it is for you. Don't listen to that. In order for this to be true, you have to be able to test it.